Well, students, in this lecture, we will learn how to write Python code for Newton-Raphson method. Again, I will use the Colab interface. Let's go to New, More, and click on the Google Colaboratory, and that will open the Colab interface. I have already written the Newton-Raphson code for myself. I will just download that program and explain you how it is coded. So to download a already written Python code, just go to File, Upload Notebook, and then browse in your folder for the file that consists of the code that you want to upload. I have chosen the Newton-Raphson code that I have already written, and now the Google Colaboratory is uploading that file. And now you can see file where I have written the Python code for Newton-Raphson method. Let us quickly recall the Newton-Raphson method. Newton-Raphson method is basically a nonlinear solver, means you are given a function f, which is generally assumed to be a continuous function, and we are interested in finding a simple root of the equation f of x equal to 0. Therefore, in our code, we have to give the information of the function f. So we will take the function expression as an input. If you recall, in the Newton-Raphson method's formula, we also have f dash. Therefore, we will take f dash also as an input, and the initial guess for the root is also taken as the input. And finally, we will take the tolerance parameter epsilon as an input to our program. Let us see the role of each of these inputs. So we are given the initial guess x0. With that, we have to generate x1, x2, and so on. Like that, the aim of the method is to generate a sequence of numbers which is expected to converge to a simple root of the equation f of x equal to 0. So in that way, we will assume that we are given xk for some positive integer k, and we have to compute x of k plus 1. Here you can just plug in k equal to 0 and see we are given x of 0 and we have to find x of 1. That is how it comes. Now, how will you find this value? Well, that is using the Newton-Raphson formula given by x of k plus 1, which we want to find, equal to x of k, which we assume to be known, minus f evaluated at xk. Again, you see xk is known, therefore we can evaluate this term also because f is already given as an input to us, divided by f dash of xk. Again, f dash is given as an input to us, therefore we can find f dash of xk provided xk is known to us. So like that, once you know xk, you can get xk plus 1. Now you see you are given x0, from there you can find x1. Once you get x1, you plug in that value on the right hand side expression and get x2. Once you get x2, again you plug into the right hand side expression and get x3. Like that, the loop will go on infinitely and generates a sequence of real numbers. And if all the hypotheses of the convergence theorem is satisfied, well, this sequence should converge. That is the idea. But as a program, we have to terminate our loop somewhere. And for that, we need some stopping criterion. Well, you can just specify a value of the number of iterations that you want to perform, and you can terminate the loop once that many iterations are done. But there is no guarantee that whether the xk at that iteration where we stopped is a good approximation to our root. Therefore, it's better to use some other criteria. Well, what we will use is this modulus of xk plus 1 minus xk is less than epsilon. Remember, epsilon is a value that is already taken as an input in our program. Now, at the end of each iteration, we will take the present iteration's value, which is computed by this formula, minus the previous iteration's value, and we will find this number. If this number is less than the number that we have taken, which is called the tolerance parameter, then we will terminate our loop. That is the idea. And this is the stopping criterion for our program. And what is the output? Well, once you stop the iteration, then declare the value xk plus 1, which is computed at the present iteration, as the approximate value for the root that we want to capture for the equation f of x equal to 0. Now, this is a kind of a rough algorithm that we have framed. Let us see how to write the Python code based on this algorithm. Well, to write the code, we have to start a code cell. For that, we have to click on this button. That will open a code cell like this. I have already written the program, therefore it is already there. Let us get into the code cell and see how to write the Python code. So as an input, we have to take the expression for the function f with which we define the equation f of x equal to 0, right? So the function expression that I have taken here is x square plus 3x minus 1.5. Therefore, my equation is x square plus 3x minus 1.5 equal to 0. And this is the format which will define an expression like this, and it will assign the notation f for this expression. So wherever if you write f of x, it will take the value stored in the variable x and computes the value of this expression. That is the idea. Similarly, we will also define the derivative of f, that is f dash, in the variable name fd. You can give your own variable name, and that is obviously 2x plus 3, right? Now, the third input, if you recall, it is x naught that we have to take. Now, what I'm doing here is I'm just defining my x as an array containing two components. The first one is for x naught and the second one is for x1. I have just initialized it as 0. Later, I will compute some value as per the Newton-Raphson formula and overwrite this value 0 by the new computed value. And finally, the tolerance parameter epsilon I have chosen as 0.0001. So our input section is over. Let us go to the iteration part. First, I'm computing x1. For that, I'm using the Newton-Raphson formula x naught minus f of x naught divided by f dash of x naught. Then I'm computing the error, which is absolute value of x1 minus x naught. Now I'm entering into the while loop where I'm checking if this error is greater than epsilon. Then I have to keep on performing the iteration till the error becomes strictly less than epsilon. That is what we have decided to take as the stopping criteria for our iterative process. If the condition is not satisfied, then you keep on doing this iteration. That is what the while loop is doing here. As long as the stopping criterion is not satisfied, this loop will keep on continuing. Now here I am supposed to compute x1, then with the help of x1 I am supposed to compute x2, with the help of x2 I am supposed to compute x3 and so on. But I am just doing a small memory management. If you see the structure of this loop, you can clearly see that once you find x1, you never use x0. Therefore, why to create one more memory for x2? We can simply use x0 to now store x1, because once x1 is computed, x0 is not going to be used anymore. Therefore, you overwrite x0 by x1, and thereby you make the memory for x1 free so that the x2 can be stored in x1 itself. In that way, you can manage your iteration with only two variables, x0 and x1. That is what I am doing. Once I computed x1, I store that value x1 into x0. Therefore, the initial guess is now forgotten and the new value x1 comes and sits in x0, and thereby the memory x1 is now free. In that, I am putting the value of x2 now. Remember, x0 is nothing but x1. Therefore, this expression actually means x1 minus f of x1 divided by f dash of x1. That I am supposed to store in x2 as per my method, but to minimize the memory usage, I am just storing it in x1. Again, I am finding the absolute error, and this is the end of this loop. In Python, while loop format is this, and whatever you type with indent like this will be considered as the part of this loop. Therefore, the first line is a part of this loop because there is an indent here. The second line is also part of the loop. Third is also a part of loop. These two lines will not be executed by the Python because these lines start with hash. Now you see this line is executed by Python. Since it is not with indent, Python will understand that this while loop ends up to here. That's all. So Python will keep on doing these three lines only under this while loop till this condition is violated. Once this condition is violated, it means if the error is less than epsilon, then it will break the loop and come out. So if you recall, we told if this condition is satisfied, then we will declare that value as the approximate value of our root. Therefore, once this loop breaks, I will come out and print that value x1 as the approximate root. I am also finding the residual error. Residual error means f of whatever is the computed value. Okay, this is just for information I am putting. I am not using the residual error for the stopping criteria, but just to have an idea of how close we are to the root in the residual sense. So this is the code for Newton-Raphson method. I hope you have understood this. Now let us run this code and see what is the root of this equation that the Newton-Raphson method captures when we start our iteration with x0 equal to 10. When we run the code for the first time, the Colab will allot some memory and disk space in its server. Therefore, the first time takes little longer. Later on, it will go on faster. Yes, it has initialized the memory and it has run the program and gave the approximate root of our equation as 0.4364 and so on. And the residual error is 5.3 into 10 to the power of minus 9. That is pretty small. Therefore, we hope that this is a very good approximation to our root as far as the residual error is concerned. Well, in this version of the code, the way we have given output, you can see that there is no idea of how the iteration went on and how many iterations were performed to achieve this accuracy. Let us try to also improve this code to get more idea about how the iteration went on. For this, let us try to update the code to get some visual output. For instance, now we would like to plot a graph with x-axis as the iteration number and y-axis as the corresponding iteration value x of k. And also, let us plot a graph with the geometric interpretation of the Newton-Raphson method iterations. Let's take the first output. In order to plot the values of xk, you see now we have to remember all the values that are computed. Right from x0 till xk, the iteration at which the stopping criteria is satisfied, and therefore we stopped the iteration, right? So we will now modify our code to remember all the iterations. In order to plot the graph, we have to import the module called matplotlib.pyplot. As we have seen in our introductory lecture, we can give a shortcut for this. I am taking it as PLT. Similarly, we have to also import another module called numpy. Now let's go into the code. The input part is the same as what we did previously. Now I'm not going to rewrite my x0 and x1 in every iteration, but I'm going to remember the values that were computed in each iteration. So for the iteration index, I will take k and initialize it to 0. Remember, in Python, the array index starts from 0 and go on, just like C and C++. Now the value 10, which I took as the initial guess, is stored in x of 0. Now you see k is equal to 0, therefore x of k is nothing but x of 0. That will hold the value 10 here. So the 10 is substituted here. And similarly, f of 10, that will give you the value of this expression at x equal to 10. And similarly, f dash of 10, again, that will give the value 2 into 10 plus 3 here. And then it will compute this expression and store that value in x1. Because k equal to 0, therefore x of k plus 1 is x of 1. And as usual, it will find the error. Once it has the initial error, then it will start the iteration and check the stopping criterion. As long as the stopping criterion is not satisfied, the iteration will go on. At every iteration, you will increment k by 1, and this command will add one more component to this array and initialize it as 0. Remember, x0 is 10. Now x1 is computed here, and that is rewritten in the place of 0 here. Now we need x2. For that, I'm again making one more memory for x2 and initializing it as 0. And now I will go to compute x2. Remember, here k equal to 1. Therefore, k plus 1 is 2. So the left hand side is x2. The right hand side is x1 minus f of x1 divided by f dash of x1. x1 is already computed here, and that is now substituted in this expression. And the value of this expression is stored in x2. Again, go to find the error. And now, ideally, I want to go back and check whether this condition is satisfied. If it is satisfied, I will do one more iteration and so on, right? But sometimes it may happen that your iteration will keep on going, especially when the iteration sequence is not converging, then your loop will never end. So to avoid that, I'm also fixing some maximum number of iterations beyond which I will forcibly terminate the loop. And in order to give a warning that I have forcibly terminated without satisfying my stopping criterion, I'm just printing this warning command, and then I'm breaking the loop. Remember, this if loop consists of these two lines because there is a further two indents here. Therefore, this if loop has these two indents, and since the if loop itself is starting with an indent, it is the part of this while loop. So the while loop's body consists of these lines, and the if condition consists of these two lines. Okay. If k is less than 250, then it will not get into this if loop. It will directly go into this while loop and start doing this 4 lines as long as this condition is satisfied. Or if k takes the value 250, then even though this condition is satisfied, it will just break this loop. That is what the break does. It breaks this while loop and comes out of the iteration and prints the value of xk as the approximate root. Of course, if the loop is broken because of this situation, then you have a warning command, and from there you can see that this approximate root may not be a good approximation at all. Anyway, we are also printing the residual error. You can see from there how bad your approximation is if you have terminated the while loop because of this condition. Okay, now comes the new part. We want to go for the graphical output. So as the first output, we want to plot the graph with x-axis as k. Remember, k starts from 0 and goes till how many iterations are done, and then the y-axis as the corresponding iteration values which are stored in the array x. Let us see how to do that. Now, how to know how many iterations are done here? That can also be obtained by seeing the length of the array x. Len of x will give you the length of the array, right? Now, I'm just also printing the values of xk here, just to see how the values went. But our aim is to actually generate a graph. Let's see how to do that. X-axis should be k. So what I'm doing is from 0 to length of x. Length of x is nothing but the number of components in the x array. And therefore, you will go from 0 to the number of columns in x with the step size 1. Therefore, x-axis will have 0, 1, 2, 3 up to how many iterations have been performed, that number it will go on. And y-axis I'm taking as x itself. You don't need this, but just to have a clear idea of how the plot goes, I have just stored this values of the iteration in a new variable called y-axis. You can directly put x here, that's not a problem. Now comes the main plotting command. Plot is not a Python command. It is inbuilt in an external module called matplotlib.pyplot, right? And that I have shortly denoted as PLT. So I'm calling that PLT module. In that module, plot is a command. So plt.plot will get into that module, take that command and execute it in the Python code. So what the plot does, it will generate a graph with x-axis as 0, 1, 2 up to the number of iterations happened, and y-axis as the corresponding x values. Other things are just to have some extra features in the graph. For instance, this graph, I want it to be in green color and the line should be in dashed, and the width of the line is 1. I also want to put a marker with the symbol O with blue color, and the marker size is 7. When you see the plot, you will understand what it is. And other things are some text. X-axis label I want to put as k, y-axis label as x of k. I'm putting $ because it will automatically print it in the LaTeX format. That is the only purpose of putting $ here. You won't see $ in the graph actually. And this is the title of the graph. Okay, let us just run this code to see the output 1 alone. Then you will understand how this plot worked. Well, the program is executed. We will go to the output and see. As we have seen, we were first printing all the values of the iteration. There were 7 iterations totally. Out of that, the first one is the initial guess itself. Then the actual iteration started from here and went up to 6. And the 6th iteration was declared as the approximate root because the stopping criteria was satisfied at the 6th iteration. The same is now represented in the graph. If you recall, I asked the graph to be in green color with dashed line. Also, I wanted the graph to be, I wanted the x values, that is the iteration values, to be marked with the symbol O in blue color. That is also done here, O with blue color. These are the values of the iteration. You can see from here, x0. So k equal to 0, x value is 10. k equal to 1, the x value is somewhere near 4.5, and x2 is somewhere 2.1, and so on. You can see the iteration started from here, it jumped here, and then it slowly started accumulating near the root. So the root is somewhere near 1.19, and so many iteration values are getting accumulated here. The stopping criteria is xk plus 1 minus xk. If that is less than some epsilon, then we are stopping. Now you can see that this value and this value in the y-axis, in the vertical sense, you have to see the difference is very much small, and therefore the iteration is stopped. The next output is to generate the geometrical interpretation of the Newton-Raphson method. Let me not explain this, but let you understand how the program is written. I will only show you the output here. Here you can see that the blue line is the graph of the function f. Let's go back and see what is the function f that we have taken. Well, for this program, I have taken my function f as x squared plus 3x minus 5. So that's a quadratic polynomial. This blue line is the graph of this quadratic polynomial, and the red line is the tangent line at x equal to x naught, that is 10, and that intersects the point somewhere here, 4 point something. If you recall, that was the value of x1, 4.56. So this tangent line is intersecting at somewhere 4.56. That is precisely this number. And then the green line is k equal to 1, that you can see coming here, and that is the tangent line at x equal to x1, and that is intersecting somewhere here, which is around 2 point something. If you see, it is 2.13. And in this graph, it is this point. Here, it is the point of intersection of this green line, which is the tangent line at the point x equal to x1, that is this, and the x-axis. And similarly, the other iterations go on.